Look at this question. A car has to move on a level turn of radius 45 meter. If the coefficient of static friction between the tire and the road is mu s, that is equal to 2.0, find the maximum speed that car can take without skidding. See, car has to move on a level turn, means the turn which he has to take is horizontal. It's horizontal plane. It has to take turn on a horizontal plane. That is what it means. Suppose this is the inner radius of the turn. This is outer radius. So car has to take turn on some part of it, right? It has to take turn like this. So when it has to take turn like this, then the free body diagram would be what? You have a normal reaction, you have mg, and on this side you have a friction, and on this side we have a centrifugal force. If I keep my observer on the car itself, if I am studying dynamics by keeping my observer on the car itself, then the free body diagram would be F is the friction in this direction, mv square is the centrifugal force, mv square is the centrifugal force. So in order to prevent skidding, this F minus mv square by r has to be 0. We want that the car should be in radial equilibrium. We want that the car should be in radial equilibrium. So in order to keep it in radial equilibrium, net force in radial direction has to be 0, right? So F is, but this F has got a maxima. This F has got a maxima. So you can say mv, the maxima of this F will set the maxima of V. The maxima of this F will set the maxima of this V. This is static friction, and maxima of the static friction is mu n. So V max square, and n is what? There is vertical equilibrium. There is no motion in vertical direction, so n minus mg is 0. So n is equal to mg. This is mu mg. So this mm will cancel out, and V max is under root mu gr, which is mu is 2, g is 10, and radius is 45. So it is 900, it is 30 meter per second. That's the maximum velocity which car can have. If car has got velocity beyond this, it will skid in radial direction, and it has got velocity less than this, then it is safe. So maximum allowed velocity is 30 meter per second. Alright, without skidding. Let's move to next question. Next question is, a circular track of radius 600 meter is to be designed for cars at an average speed of 180 km per hour. What should be angle of banking of this track? Okay, we already read what is banking. The road is made a bit inclined, so that a component of normal reaction comes in radially inward direction in order to balance centrifugal force. So if I keep my observer in the frame of car, then the free body diagram would be what? Free body diagram is, this is mg, you have normal reaction, and on this side, the car has to take turn like this. All right, it has to take turn like this. So on this side, this is track, radius of the track, which is say r, and r is 600 meter. This is mv square by r, and in order to prevent from skidding, we'll have a component of n which will balance mv square by r. So if I take my coordinate system like this, like this. This is the x-axis and this is y-axis. So this is the x-axis and y-axis. Then this is theta, and this will also be theta. This will also be theta. So I want that there should not be any skidding in radial direction. So in vertical we have equilibrium, so we have n cos theta equals to mg, and this mv square bar, this theta should be such that this mv square bar should be balanced by the component of n which you have in radially inward direction. This is a track, right? So I want that this there is no radial motion, there is no skidding. Radial motion means it will skid. Radial motion means it is going to skid, right? I want the vehicle to move in this direction, in this way, right? We have a circular track, and we want that the surface of the track should be banged. We want surface of the track should be made bit inclined, so that normal reaction, a component of normal reaction should come in radially inward direction, as should balance this n sin theta should balance mv square by r. Alright, so from this, if I call this 1 and this is 2, the radial, this is equation of radial equilibrium. There is no radial acceleration, right? If I keep my observer on the car, and if I do this question from the frame, from the inertial frame, then that will say that you have n sin theta force in radially inward direction, that would be equal to mass into centripetal acceleration. That's the other way of looking at the same equation. See, the same equation can be seen as, if I consider inertial observer, then from inertial observer, this car, this vehicle, this car is moving in a circular track, and hence it is accelerating in radially inward direction with v square by r. So mass into acceleration in radially inward direction equals to force in radially inward direction. But if I take my observer on the car itself, then this is non-inertial observer, and since he is non-inertial observer, in order to study dynamics, you have to apply a pseudo force also in direction opposite to the direction of the frame of direction of the acceleration of the frame of non-inertial observer. Car is what? The man is in car frame, so car is accelerating radially inward direction, so you have to apply a pseudo force in radially outward direction, and that's a pseudo force, and this pseudo force has to be balanced by n sin theta. There is this person, see, there is a basic difference in observation of the person on the ground and the person on the car. Person on the ground is seeing that the car is moving car is moving in circular motion. Car is undergoing a circular motion. So undergoing circular motion is car is accelerating radially inward direction, whereas this observer O2 on the car, he is going to see the car to be at rest. The observer O2 on the car is going to see car to be at rest, right? So but if you want to correlate his observation with the forces, then apart from all the real forces which is acting on this car, you have to apply a pseudo force also. So this is pseudo force if I think as per observer O2, but if I think as per observer O1, then you don't have to apply this force. The only force is this n mg and so on. So we have n cos theta balancing mg, and n sin theta would be a force in radially inward direction, and that would be equal to mass into acceleration of the car observed by O1, because O1 is inertial observer, O1 is outside this car, so he is going to see the car moving in circular motion. So moving in a circular motion means accelerating radially inward direction. So this is the acceleration radially inward direction, and this is net force radially inward direction. So this equation can be seen both way. I can see this as n sin theta as the force in radially inward direction equals to mass into acceleration observed by O1, or I can see it as n sin theta equals to centrifugal force. We will call it centrifugal force if we are doing question as per the observation made by O2. Be very clear. We will call this centrifugal force. We will call this centrifugal force when if I am doing question as per the observation made by O2. In that case, it is centrifugal force. But if I am doing question as per the observation made by inertial observer, this is going to be mass into centripetal acceleration. I hope you understand. Centrifugal force is pseudo force. This is required only when you try to do the question from the question as per the observation made by a non-inertial observer. If you are doing the question as per inertial observer, you don't need centrifugal force. Centrifugal force is pseudo force. It's not a real force. It doesn't arise out of interaction. Alright, so we can write this as, if I divide 1 by 2, that is tan theta will be VRG. So what is the velocity you need to manage? 180 kilometers per hour. So 180 into 1000, 13600. This 0 will cancel out. So you need to manage 50 meter per second. 50 square, right? And radius is 600 meter and G is 10. So this is going to be 25, or this will be 2. So 5 upon 12. So theta is tan inverse 5 upon 12. Alright. So this is how we can do it. Tan inverse 5 upon 12. Okay. So that's the angle by which the road has to be banged. That's the angle by which the road has to be banged. Alright. Let's move to next question. See this question. A particle of mass m is suspended from the ceiling through a string of radius of length L. The particle moves in a horizontal circle of radius r. Find the speed of particle and tension in the string. Let me draw the figure first. So it is like this. You have a body of mass m, say, is suspended from the ceiling, and this m undergoes a circular motion like this. It undergoes a circular motion like this. Say this is angle theta. Alright. This is called conical pendulum. This is called conical pendulum. Alright. So what are the forces acting on this particle? See this. First of all, you have to decide that you have to do question as per inertial observer or non-inertial observer. We can have two cases. Say suppose observer is outside, observer is inertial. We have, say, O1 is inertial observer. First of all, let me try to do this question as per inertial observer. As per inertial observer, O1 is inertial observer. O1 is observer who is inertial, non-accelerated. So what O1 is going to observe? O1 is going to observe this body moving in this kind of circular motion. Circular motion of radius. This is L. This is L. And this is L sin theta. L sin theta. So what are the forces acting? Forces acting are, you have tension T. So this is theta. So I take this coordinate system x and y. So this is theta. And you have mg, force mg, right? Anything else? No. This is only force acting. Alright. So in y direction there is no acceleration in y direction. So t cos theta mg is 0, and you have unbalanced force in negative x direction, that is in radially inward direction. You have a net unbalanced force t sin theta, and since this body undergoes a circular motion, so it will it undergoes a kind of acceleration radially inward direction. I told you earlier also, if a body is undergoing a circular motion, it is accelerating radially inward direction. So net force is radially inward direction is t sin theta, and the acceleration radially inward direction is m v square upon L sin theta. V square upon R. R is L sin theta. Right. So this is the equation. Right. This is the equation. If suppose somebody, I take an observer who is on this body itself, then this observer, since he is on this body of mass m, then in that case he would be inheriting all the motion of mass m. So in a way he is also undergoing a kind of circular motion, and hence he is accelerating radially in inward direction. And what is his observation? Since he is on the mass m, he'll find mass m to be at rest. He'll find mass m to be at rest. But in order to correlate his observation with the forces, apart from all the forces which he is acting, I have to apply one pseudo force also. I have to apply one pseudo force, and that pseudo force would be equal to mass of this body into centripetal acceleration. Centripetal acceleration is v square by L sin theta. So again, you'll have this observer observing this to be at rest. So it is in vertical equilibrium as well as radial equilibrium. So vertical equilibrium is this equation, and radial equilibrium is the net force in radial direction is going to be 0. So this is going to be 0. This equation, same equation. So whichever observer you take, if you take O1 inertial observer, then this is mass into acceleration, mass into centripetal acceleration. If you take O2 observer on the mass itself, then this is non-inertial observer. In that case, this is centrifugal force. This is centrifugal force, mv square by r. mv square by radius of the circular motion, right? So there is other way of seeing the same thing, same term. This is seen as centrifugal force if I am doing question as per O2, and this is seen as mass into centripetal acceleration if I am doing question as per O1. I think you get this point, right? So L sin theta is given to you. L sin theta is R. L sin theta is R. So this factor is R, right? So from here we have T cos theta equals to mg, and T sin theta is mv square by r. So if I divide 1 by 2, then I get v square by rg, right? And what's tan theta? See, from here sin theta is r by l. So tan theta would be r upon l square minus r square. So v square is r square g, or v comes out to be r root g 1 by 4. Alright, this is the velocity. And tension you can find, say from here, or from here you can find out. Tension is mg by cos theta, and sin theta is this. What is cos theta? Cos theta is going to be this. So that means this is going to be mg L upon this, right? So that's your tension. That's the tension. Okay. So you have tension T, and you have velocity V. That's how you can do this question. You have to keep in mind what I told you about this O1 and O2. Centrifugal force is pseudo force. It's not a real force. It is required only when you do the question as per the observation made by non-inertial observer. Be very clear. Okay, let's go to the next question. In a rotor, a hollow vertical cylindrical structure rotates about its axis, and a person rests against the inner wall. At a particular speed of rotor, the floor below the person is removed, and person hangs resting against the wall without any floor. If the radius of rotor is 2 meter and the coefficient of static friction between wall and the person is 0.2, find the minimum speed at which the floor may be removed. Let me first draw the figure. So this is the rotor, and the radius is 2 meter. It's 2 meter. And say you have the person over here. You have the person over here, right? So he resting against the inner wall. He resting against the inner wall, and you have started rotating. You started rotating with say omega. Okay, rotates. Suppose omega is the angular velocity. Omega is the angular velocity. Omega is the angular velocity. And at a particular speed, the floor below the person removed, and person hangs resting against the wall. So when the person is hanging resting against the wall, he is not falling in downward direction. So what's the free body diagram? Let me draw the free body diagram. See, you have a, let me take this pen. So you have mg force acting, and you'll have a friction force, say F is the friction force, static friction, of course, static friction, and what else you have? If suppose I take my observer over here itself, I take my observer on the rotor itself. So what's the observation made by this observer? It's a non-universal observer. If I take my observer on the rotor itself, he is a non-universal observer, right? So he is going to see this person to be at rest, and he is himself accelerating. So in order to analyze the dynamics of this person, he will apply a centrifugal force. Centrifugal force is going to be m omega square r, and r is 2 meter, right? But the motion of this body is constrained in this direction, so you have a normal reaction. Motion of this body is constrained radially outward direction, so this cylinder, this rotor, is going to apply a normal reaction in radially inward direction, right? So we are trying to correlate the observation made by this observer for this person, right? So this person is in vertical equilibrium, and this person is also in radial equilibrium, because this person will see, say this observer O2 is going to see this man to be at rest. If I take observer outside, then he is going to see this man moving in a circular motion. But if I take an observer attached to the rotor itself, then he is inheriting all the motion of the rotor, and he will see this person to be at rest, to be in radial equilibrium, right? So if I do the question as per inertial observer, in that case I don't have to apply this force, because this is a pseudo force. But if I do the question as per observation made by O2, then you have to apply this pseudo force. Are you getting my point? Then you have to apply pseudo force. In both the cases you can do the problem. Say if I write the equation as per O2, then I have what? mg minus f is 0, and since for O2 this person is in radial equilibrium, it's not moving in a circular motion for O2 himself is attached to the rotor. So a observer attached to rotor is going to see this person to be at rest. He won't be seeing this person to be in circular motion, so he'll say it is radial equilibrium. So net force in radial direction, that is m omega square, is 0. If I write the equation as per the observation made by O1, if I correlate the observation of O1, then if I want to correlate the observation made by O1, I don't need the pseudo force. Then his observation is what? What is the observation of O1? He will see rotor to be moving in circle. He will see rotor is rotating. He will find the rotor to be rotating, and this person who is resting against the rotor is also rotating in a circular motion. He is also moving in a circular motion. So in a way, he is accelerating radially inward direction. So net force in radially inward direction is n, and that would lead to mass into acceleration. This is centripetal acceleration, because O1 is finding this person moving in a circular motion. So person moving in a circular motion means he is accelerating radially inward direction, right? And he will also find this person to be in vertical equilibrium. So you have F minus mg is 0. So you got the same equation. The equation will be same. See, this pseudo force compensates for the difference in the observation made by O1 and O2. That's what pseudo force stands for. It compensates for the observation difference in the observation made by inertial and non-inertial observer, right? So whatever observer you take, your equation will turn out to be same. Getting a point? And the question asks for minimum speed. See, you want to find omega. So we have what here? We have here n. We want to find n, right? So this is F and m omega square. The minimum speed should be such that this F should balance mg. And what is F equal to? The maximum value of F is equal to mu n, right? I want omega to be minimum, right? I want minimum value of omega such that this person does not fall. So the maximum friction which you can have is mu n, and I have omega square r is n. So we can write this, we can divide by this, we can divide this. So we have g upon omega square r is mu, or omega is g upon mu r under root. Alright, that's the omega, that's the omega. And velocity, if you want, then that velocity for a person moving in a circular motion, the velocity is omega r. So that will come as g r upon mu. That's the minimum speed which you must have, right? Only then you can remove the surface over here. You have a surface, you can remove it. The person will not fall. The person is not going to fall. Alright, so this is the way you can do. Let's take the next question. See this question. A metal ring of mass m and radius r is placed on a smooth horizontal table and set rotating about its own axis in such a way that each part of the ring moves with a speed v. Find the tension in this ring. Find the tension in the ring. See, you have a ring. You have the ring. This is the ring. And this ring is rotating. This ring is rotating about this axis, say with omega. So when the ring rotates, if I take this element of the ring, then each point on the ring is undergoing a kind of circular motion. Each point on the ring is undergoing a kind of circular motion. See, if I isolate this part of the ring, say this part of the ring, let's call it ds, and we can see this ds in terms of, say, it's the element of the ring. This is the element of the ring, and let's call say call it d theta. So this ring will be, the length of this element will be r d theta. See, if I only consider the free body diagram of this element of the ring, since this element is the part of ring, so this must be interacting with the rest of the ring. This element must be interacting with the rest of the ring. This is the part of ring, so rest of the ring must be attracting this. Only then this can be a part of ring. See, if you have a rod like this, if I break this from here and try to draw the free body diagram, not break this, if I just imagine a partition of this rod, say L1 and L2, and then I draw the free body diagram. Since this L1 and L2 are together, so they must be attracting each other. They must be attracting each other. L1 must be attracting L2, and sorry, it's not like this. L1 must get attracted towards L2 and L2 must get attracted towards L1. Only then they can remain together. They are remaining together means, if I consider the two halves, then L1 must attract L2 with certain force F, and L2 must attract with certain force F on L1, right? So since this ds is part of the ring, so rest of the ring must be attracting it. Let's say force T over here and force T over here. This must be, this part of the ring must be attracting ds with force T, and this part of the ring must be attracting from this side with force T, and T is nothing but tension. T is nothing but tension, right? So if I draw this, then this is going to be d theta by 2, so this must also be d theta by 2. That's a simple geometry. If I draw a tangent over here, it is perpendicular to this, so and this tangent is perpendicular to this line, so this line and this line angle is d theta by 2, so this line and this line is also d theta by 2. So I have a line, I have this tangent, I have this line, say r, and this is my tangent. So if I rotate this line, radius like this and tangent like this, so with whatever angle I rotate this radius, by same angle the tangent gets rotated. So we have this tangent to this tangent perpendicular to this radius, and we have this tangent perpendicular to this radius. So if radius, the angle is d theta by 2, between tangents the angle is d theta by 2. Getting a point? Okay, so the horizontal component will cancel out, the vertical component will add up, and vertical component will lie in radially inward direction. So you have t sine d theta by 2, t sine d theta by 2 plus one more force of the same magnitude. So net force in radially inward direction, and since this part is undergoing a circular motion, so undergoing a circular motion is what? It must be accelerating in radially inward direction. With what acceleration? With acceleration equals to omega square, or v is given to you, so I write v square by r. Right? This is mass into centripetal acceleration. Mass into centripetal acceleration. If I keep my observer over here, then he'll find this element to be at rest, and then he'll apply a centrifugal force. I will say it is radial equilibrium, so net force radial inward direction will be equal to centrifugal force acting radially outward direction. So you understand the trick? The equation will be same. See, for observer outside, this ring is rotating, and hence this element of the ring is also undergoing kind of circular motion. So since this element undergoes a circular motion, then net force in radially inward direction will be equal to mass of this element into acceleration in radially inward direction, because we have already proved this fact that if a body is undergoing a circular motion, it is accelerating in radially inward direction with v square by r. And what is dm? This is 2t sine d theta by 2, and dm is what? Mass of this element, that is m upon 2 pi r into r d theta. R will cancel out, and this d theta is very small, so sine d theta by 2 is d theta by 2, so that is m d theta upon 2 pi v square by r. So d theta will cancel out, 2 will cancel out, so tension is mv square upon 2 pi r. Getting a point? That's the tension. That's the tension developed in the ring. That's the tension developed in the ring. Alright. Now let's look at this question. A table with smooth vertical surface is turning at an angular velocity, angular speed omega about its axis. A groove is made on the surface along the radius, and a particle is gently placed in the groove at a distance a from the center. Right? Find the speed of particle with respect to table as its distance from the center becomes L. Suppose I keep my observer over here itself. So he is a observer in rotating frame. So when we draw the free body diagram, see there are many forces acting over here. You have mg normal reaction. In fact, you have normal reaction. You have this mg. You have normal reaction n. In fact, you have two normal reaction n1 and n2 from left and right, also from the left wall of the groove and right wall of the groove, right? But groove will constrain the motion of this body. It cannot move in this direction and this direction. It has to move along the groove only. It has to move along the groove only. And also, see, if I take my say this is x, y and z, right? So in positive z direction you have normal reaction n, and if I draw the free body diagram of this, we have what? We have x, y, z. So z is perpendicular to the planes, so the forces are on this particle. You have a force in positive z direction, which is normal reaction, and a force in negative z direction, which is mg. You have a force in positive y direction, from positive y direction, which is normal reaction n1, and you have n2 also. The n1 and n2 are the two forces. n1 and n2 are the forces from the left and right wall of the groove, and they will balance each other. n1 and n2 will be equal, and you have n force in positive z direction, you have mg force in negative z direction, so they will also balance because there is no motion in z direction. And there will be one Coriolis force also, since the observer is lying in a rotating frame, 2m omega cross v, and omega is in outward direction and velocity will be in this direction because this is the only possible direction. So omega cross v will also be perpendicular to the groove, because the only motion which is free is along the groove. So if you have velocity along the groove, then omega cross v will be perpendicular to the groove, so that motion is constrained. So then Coriolis force will not lead to any kind of motion. So the only motion which is free is along x, and along x, what's the force? Force is m omega square x. If x is the distance of the particle from center, if x is distance of the particle from the center, the only force is m omega square x, and that will lead to motion in x directions, dv by dt. So mm will cancel out, so this dv by dt will be equal to v dv by dx, or I should tell you how this v dv by dx. This is dv by dx omega square x. So this dx by dt is v, alright. So this can be written as v dv, and integrate it. When x is at a, the velocity is 0, and you want the velocity when x is L. So this is v square by 2, 0 to L, sorry, 0 to v, and here you have omega square x square by 2, a to L. So that means v square is omega square L square minus a square, or v is this force. Alright. So due to this centrifugal force, the body will be moving in radially outward direction. Due to this centrifugal force, the body will be moving in radially outward direction. Okay. Thank you very much.